In this section, we'll focus on working more problems about linear equations. In the first part, we'll review the equation of a line. Then, in the second part, we'll determine if lines are parallel, perpendicular, or neither, given certain pieces of information. And then finally, in the last part, we'll see what a linear function looks like when it's increasing or decreasing. Moving on to part A, we saw in recent sections different equations for a line, such as point-slope form and slope-intercept form. The point-slope form of a line is given by the following equation, where the letter m represents slope and y1 and x1 correspond to values of a point. To find point-slope form, we need one point in the slope of this line. The equation for slope-intercept form is given by the following. Again, m represents slope, and b is our y-intercept. To find the slope-intercept form of a line, we need two pieces of information again, and that's just 2 points that lie on top of the line. Once we have these 2 points, we find our slope, again with the slope equation, and then we find our y-intercept. Now, let's find the slope-intercept form of a line. In example 1, we want to find the slope-intercept form of a line whose x-intercept is -2, 0, and whose y-intercept is 0, 4. The first thing to recall is that every line is determined by 2 points. Then, even though the problem gives us the x-intercept and y-intercept, it still gives us 2 points, and so we can find the equation for this line. First, let's find slope. Slope is given by m is equal to y2 minus y1 divided by x2 minus x1. Here, we'll let the x-intercept be our x1 and y1, and we'll let our y-intercept be our x2, y2. Plugging this in, we'll get 4 minus 0 divided by 0 minus a -2. Simplifying, we see 4 remains on top, and on the bottom we get a 2. So this is going to be equal to 2. We're looking for the slope-intercept form, so the equation we'll be using is y is equal to mx plus b. We just found what our m is. Writing this out, we'll have a 2x plus b, but recall that b is our y-intercept. And we're given the value for our y-intercept already, which is the point 0, 4, which means the value we want to plug in for b here is 4. So the equation of our line is going to be 2x plus 4. Let's now turn our attention to the reverse problem. Suppose we're given the equation of a line. Let's go ahead and find the x and y-intercepts. Here, we're given the line 50x minus 46, and we want to find the x and y-intercepts. Let's go ahead and recall just the intuitive definition of an x-intercept. The x-intercept occurs on the graph where the graph intersects the x-axis. This occurs when y is equal to 0. To solve for the x-intercept then, we replace our y values in our equation with 0. 0 will then be 50x minus 46. Solving for x, we'll get 46 divided by 50 is equal to x. So the point of our x-intercept is given by 46 divided by 50, comma 0. Now the y-intercept occurs where the graph intersects the y-axis, and this is going to occur exactly when x is equal to 0. Then, setting x is equal to 0 in our equation, we'll get y is equal to 50 times 0 minus 46. Simplifying, we get y is equal to a negative 46. Then the point on our graph, which is the y-intercept, is going to be the point 0, comma, negative 46. And we have our solutions. At times, we won't always be given 2 points on the graph, or the slope of the graph. Instead, we might be given other information. Let's work an example of this type. In example 3, we want to find an equation, any equation, either point-slope form or slope-intercept form, of a line that's parallel to the following. And further, passing through the point 2, 6. Given this information, we only know a point on the graph and a line that's parallel to what we're trying to find. We need to recall what it means to be a parallel line now. So we say two lines are parallel if they have the same slope. Well, in this case, the parallel line we're given is y is equal to 3x minus 5, which means the slope of our parallel line is 3, and then the slope of the line we're trying to find is also 3. We have the slope, and we're also given a point on the line, so we can just go ahead and plug this into point-slope form. Point-slope form is again given by y minus y1 is equal to m times x minus x1. Plugging in what we have, we'll get y minus 6 is equal to 3 times x minus 2. We found an equation for a line, so this is as much as we need to do. But let's go ahead and find the slope-intercept form. To do that, we can go ahead and solve this equation for y. Subtracting a 6 from both sides, we'll get a 3x minus 6 plus 6 is equal to 3x, which means the slope-intercept form will be y is equal to 3x. To finish off this section, let's talk about the graph of linear functions. Both point-slope form of a line and slope-intercept form of a line contain important pieces of information about the line itself, namely at least one point and the slope of the line. This is useful and makes graphing these types of equations very easy because all we need is one point and then the slope will give us a direction to go in. Let's see how to do this. Number one, let's go ahead and look a little more closely at the definition of the slope of a line. Again, the slope of the line is given by the difference in the y values of 2 points divided by the difference in x values of 2 points. Another way to say this is that this is equal to the change in y divided by the change in x. This information gives you a measure of what's going on. How fast are your y values changing per given unit of your x values? Let's go ahead and look at two examples. Example number one, let's see what's happening when the slope is given by 3 divided by 2. And we'll also look at the slope when this is equal to 1 divided by 4. When our slope is 3 divided by 2, this is telling us that for every 2 units that we're moving over in the x, we're also moving by 3 units in the y direction. Let's go ahead and look at a picture of what's occurring here. If we start at the point 0, 0, then a line with slope 3 divided by 2 will act as follows. Every time we move over 2 units in the x direction, we're also moving 3 units in the y direction. Another way to say this is that our y values are changing faster than our x values. So for every 3 y values we move, we're also moving by 2 x values. Now let's go ahead and look at the slope of 1 divided by 4. In this problem, our x values are changing much faster than our y values. And so we're moving 4 units in the x direction for each unit we're moving in the y direction. then the direction of our line is moving in this sort of manner. Now, once we think of our slope as the direction of our line, all we need is a point on the line, and then the slope is going to point us in the way our line is going. Let's look at an example using one of these slopes. Let's sketch y is equal to 3 divided by 2x minus 1. Again, this equation is giving us a point on the line, namely the y-intercept, which is the point 0, negative 1, and the slope of the line is giving us the direction of the line, where the slope is given by 3 divided by 2. So while we can't draw this entire line, we can draw how it behaves. So let's go ahead and look at the behavior of this line. Again, suppose we're given the x-axis here and the y-axis, and let me go ahead and draw some units. Okay, so now we have our xy axis with units drawn in. And remember, what the slope is telling us is that we're moving over 2 units in the x direction for every 3 units in the y direction. So the slope of our line is given by the blue arrow. Now, we know a point on the line is given by 0, negative 1. And so we know a point, and we know the direction of the line. So what we can do is drag the blue arrow onto the point 0, negative 1, and then just extend it in both directions. So by extending this in both directions, we see that our line looks something like this. This is the end of part A.